Hi there, this is Old Dude with a Pulse, and today we are talking about 3D printing a rack and pinion. And the rack we designed is something like okay, here's the rack by itself. It's maybe let's put the light over here. Like this. It's a double rack because when you print in plastic there's some flex to it. It's then designed to be bolted or used to something. That's what the things are on the bottom. And we also print it in one piece together with one of our frame pieces. You can use it up to climb, or when you do this, you're going to use and you reinforce it with something hexagonal, half inch hexagonal, either steel or aluminum, that goes into here and then gets held in place with some brackets. And you still have a flex here, that's why a little bit of flex, that's why we didn't design on a single rack, but a double rack where there's two pinions that hold from each side, so there is no deflection in either way, and you're just going to have a straight pull down, and this will pick up a robot and probably more. This particular piece is built out of ABS, printed out of ABS, and we have quite a few of them that goes into our system. Let's look at some of the basic layouts. I'm going to turn this off and move the camera. Okay, we made a basic sketch here. If you look again at our rack, then this whole thing is 267 millimeter long. Everything happens in our system at 26.7 millimeter increment. So for every 26.7 millimeter or 53.4 here, we have, for every 53.4 we have 10 teeth, 5 teeth for 26.7. That gives us a pitch length of 5.34 millimeters here. So as we are working for our printer with the overprint with a backlash of about 0.1 on every 0.2 on everything, we have this distance here 0.2 greater than this, so this is 5.34 divided by 2 minus 0.2, so that's 2.67, 2.47, and this is 2.87 to get the 5.34. Now we have DA, D and DF, which we get from Inventor. We'll show that later. D is the pressure, D is the pitch circle, and D and DF at the bottom of this, at the top of the teeth. We want to have a little gap here, of which we calculated of about 0.35 millimeter, so we don't bottom out with the teeth, so we have a nice, smooth and accurate running. The angle here, the calculated angle which we get from Inventor 2 is 22.8. I'm not going about the math, how to do it all with the math, or this is going to be a 5-hour video. Inventor does a lot for us, and the main intention of this is to go along with the kit. So that means we have, to get kits, that means we have about 4 millimeter from top to bottom, which we're going to see in our drawing. We're going to have a line here of 22.8 millimeter, and we have this here roughly 0.2 millimeters longer than this is here. Okay, so now let's look where we got the numbers from in Inventor. Those here where we have took the difference divided by 2 because we work with the radius. There's a 2 on each side, so those are the half sides. So you can go over this math if you want to. We're going to do some more when I edit it together with the video from that I captured directly from Inventor. Okay, we are in Inventor here, and we started off creating an assembly, and I called it Pinions, and I created some gears. Okay, we decided on 17 tooth gears. What's going on here? And I decided on a 1-to-1 ratio because that makes it easier. The center distance 28.895. If you remember, we had 5.34 for the pitch length. If I multiply this times 17 and divide it by pi, I get the diameter of 28.895 millimeter. You can then, because we don't want an offset, if I just go in here and I go collect the module and I put in this center distance and I hit calculate, I get a 1.5 millimeter because Inventor rounds it up and it gives me a unit correction. That makes things more complicated, so we are not going to do that. Okay, so you either can use a lot of math to get to it, or you just can play with the module to get the center distance, the desired center distance for this gear. Now if you look here, you have the measurements that we took down, the A, D and the F. The D is the important, that it is the circumference, the pitch circle, which has to match up the rack. So again, we went 26.7 divided by 5 gives us 5.34, and then a gear is basically a rack that's turned into a circle, so the pitch length is 5.34 times 17 tooths gives us 80 something, divided by pi, because the circumference of a circle is the diameter times pi, gives us a diameter of 28.895 millimeters. So that's how we got to this pitch here. So if we make a tooth in Inventor, you would right click on this. I make a gear. You would go to export the tooth shape. Okay, you would decide if it's the pinion or the gear. You would put in a backlash, which the backlash, you probably don't want a backlash, but you need a backlash because you have an overprint in the printer. For our printer, it's 0.2 is a good backlash. So you put this in here. Inventor does basically pretty much everything for you. Now you have the gear here, so I usually go and into the sketch and just for my write it down and keep the outside diameter just so that I have a node on it. Okay, because I'm gonna need it in a circle. I then go and I make a coil. I select the I think I selected everything. Okay, coil. Let's turn this a bit more here. Okay, then the axis would be the Z-axis, and the coil size would be the diameter, which is 31.839. 31 times pi times tan 60. It's actually the cotangent 30 because we want to have a 30-degree angle, and we gotta go here. You see it draws it up, we want to go the other way, so we turn it around and we set it to cut. Okay, and there, now we have our first gear. I usually go put a little fillet on top of it for a gear like this. It's usually 0.4 plus 0.1 per each millimeter pitch, so this is about a 0.5 here. Takes care for the overprint when the printer moves out, plus it makes it run a little fillet, makes it run a little bit smoother. So okay, and then you just go to a circular pattern. You select the coil and the fillet. Okay, you select the rotation axis, which is again the C axis, and we are going to put, I think we had 17 teeth on this one here, and you did the typing wrong. Circular pattern, coil, fillet, C axis, 1, 7. Okay, that's better. And this is how you make a gear. Inventor takes a while of doing that, so, and this computer is not so fast. Then to make the double helical gear, you just derive both gears. We can go over that too. Okay, file, save as, let's call it temp. Okay, now to make the finished gear, you just would make another new metric, because we're printing, everything's got to be in millimeters. You go derive temp, okay, and you derive it again. And you mirror it, and there you have your herringbone gear, and now you just combine those two, and you are ready to put some holes or something into this. Okay, so now let's look at the rack, okay, which is this rack here. Okay, what we did is it's quite a little cumbersome and time consuming to draw, so that's why I'm just going to go with this. You draw a sketch, and you draw one tooth. We have the other tooth the opposite. Now those are the measurements we just went over before. You have the 4 millimeters from the top to top. You have the 6 millimeters here because we space them apart by 2 millimeters. You have again 4 millimeters from here to here. You have the 22.8 degrees. If you remember, we looked at the this here. It gives us the 22.7959, which is 22.8 degree in this here, which is the tangential pressure angle. Okay, for that which is the derived value here for this, and So we are using this on the rack. That's a 22.8 degrees here, and this valley is bigger. That's why those up here are smaller than those down here, to take care of our overprint, because when we print, when it squishes together the layers, it pushes out a little bit here, and it's also pushing out a little bit here, which is this side here is this side here, and this side here is this side here. It's just on the other side. So then after we basically draw this out based on the drawing the little sketch that I showed early, the little freehand sketch that I showed early, we then on a different level draw our line. We calculate using Pythagoras how long this line has to be for the length of our gear, which in this case comes out for the 8.083. We want to have a 30-degree angle here. We want to have that's then a 60-degree here, because this is a 30, 60, 90 triangle. If you'd imagine a line here and here, and we start now. We can make a sweep. If you look at the parameters of the sweep here, it's just a standard sweep which selects those two sketches, and we just create a sweep. Okay. Next thing is we are placing a fillet on the side, just so we so at the end that we don't have any sharp corners we need to clean up. Okay, this fillet is a very small fillet because that's all we can do. It's just here for the purpose of taking care of the overprint of the printer. And this again, if we would work with metal, we wouldn't need one. If we work with a printer, we have to make some adjustments based on the printer. Okay, so now that we have those, we then make a rectangular pattern. We made 52 at 5.34 millimeter spacing, and we are getting this whole line, and then the last extrusion we do is we cut off the ends to cut it down to the lengths that we want it, so that it can, if you look, this one here is cut right at the beginning when it goes up, and this line here is at the same position here, and if you go here you have the 267 millimeters, which we want 10 times 26.7 millimeters what our bracket that we mounted to is going to be, and we cut those pieces off and we wind up with this piece. Okay, now if I create a new part there, and again, like with the gears, I derive the what's it called, double rack 1492. Okay, and again, then I derive it again, and I mirror it. Okay, and I combine. So now I have my herringbone double helical, or whatever you want to call it, double rack, like we have it, and the gears are offset. That means it only works with, if we want them on the same axle pressing together, we only works with odd numbered teeth. That's why we have a 17 tooth gear. So what we did is just to cancel. No, we don't want to save that. We already have that. Let's close this. So we then built this rack out of it, and we also made that's not the one. Yeah, this was an earlier version, but something to hold the bearings. Okay, our current version the big one. Yeah, I'm just switched to Inventor 2019, so it has to convert some of the item. Looks like this. So you get a 1/8 inch bearing in here, 1/8 inch bearing in here. Those are center spaced. If we look at the second gearing here, which has the bigger distance to line up with the bearings and line up with the bearings, which comes out to this pitch. We use the same number of teeth and come out with a new pitch, and then we have okay, that's in the end look like this. So the rack goes between the two small gears, and the two big gears mesh with each other, so we only have to power one axle, and the other axle, this gear then powers another gear that is next to it, like this. That is the mirror image of this gear printed, and on top this interacts with one side of the rack, the other gear next to it interacts with the other side of the rack, and now we have this bracket where you can either mount two in here or two here and two here with a gear that reverses them and keeps them both moving. For heavy duty application, you have 4 gears engaging with the rack, and that will lift the robot. Okay, we also have just a smaller, less yeah, just a basic 1-for-1, just one set of wheels. This thing inside here is just a support for the arch, which gets broken off out of when it's 3D printed, and it gets cut out, and you see it's the same design, the same frame design, based on the same frame design that we have, so it becomes like a building block for us. Thank you. I hope you found this little instructional video helpful to making rack and pinions with a 3D printer. Something in this, like this. Please support Team 1989 either through the website or through Patreon or this channel here. The details are in the description of the video. Thanks for watching.